So maybe we can look at Marcin's post.
Yeah, that would be great. I tried to read through it, and like I basically was just skimming over the Scala code because I just, you know, that's the part that is the blocker for me. And like the ideas make sense, but looking at the actual code is not where I feel like I have the highest level of understanding.
So if you like, maybe I can go quickly to the code, and I can say what I think, you know.
Okay, so can I say one thing before we jump into that?
Sure.
Would this be better for you and I to coordinate like another meeting to go through this stuff? Because it might be a good idea for me to like try to understand this in a lot of detail. And I have a feeling that if we jump into it right now, we might spend the rest of the time doing this, which I'm totally fine with, but then I'm not going to say anything about TLA plus today.
Well, I don't want to go any deep into this.
Okay.
I just want to point some, you know, some obvious stuff.
Cool. Yeah. I'm totally.
I don't want to go to but I'm totally that we can talk, you know, separately.
Yeah. That would be helpful for me.
I just want to emphasize that this is like some kind of interface with different methods that will work on this F type, for example, and this F type is can be some kind of state or whatever. It's
okay.
You know, whatever you want. So if we model in TLA, if you have this kind of specific methods or like state changes, right? Transitions. Yeah, exactly.
Yeah.
So each of these methods can be like one transition.
Right. Yep.
So what Marcin is saying here, how to test this, and what he is explaining is the behavioral test. So the unit test is the unit test could be, you know, you're just calling this method and you are expecting some result, and this is like unit test. But if you want to test how these methods work together, right? If you call one method, then the other, then first, then with different parameter, this is like behavior.
Okay.
So
and they do some like randomized sequence of like different calls and all the methods or something. I mean, I guess I don't know how that works, but.
Well, what you are testing, you have this interface, and your code, what you are expecting to do. Will be probably it will include more calling more than one of these methods. So you want to be sure that you can call these methods in some order that you know you're recognizing it's fine and it's correct.
Right. Yeah.
So from that perspective, I was thinking, okay, if you can specify transitions in TLA, maybe we can say, oh, can we just generate all of these transitions as interface in Scala, and we can do the same thing as you are doing in TLA. And how can we be sure that this is work? We have proof in TLA.
Yeah. So okay, so my understanding of what you're saying then is that we might be able to do something like modeling the traits that we're working in Scala in TLA plus, or at least that's kind of the idea.
This timeless model is really specifying this trait. With this F abstract.
Right.
So what he's saying here is, you know, this is some kind of test. We are calling save, which is one transition, then you're calling find email, which is another transition, and then you say, oh, this must be the same as, you know, the same as just packaging up the first
Oh, yeah, yeah. Okay. And so like this like less than minus greater than thing, the double-headed arrow is like these should be equivalent.
Equivalent, yeah.
Yeah. Okay. And so then the way that they test the equivalency is by running a bunch of random tests on one and random tests on the other, and then just checking that they all work out.
That's the point of this generative testing.
Yeah.
How you can you know generate all of these cases, and so and we don't need to do this because, you know, you will write a TLA specification which will, you know, check all of the possible changes.
Right.
So if translation to Scala is just by saying, okay, first call save and then find email, okay, we will not have proof in Scala, but we will have proof in TLA, and we have like one-to-one translation to Scala from TLA.
Yeah. So I guess my main concern is probably like too alarming of a word. You know, it's not really a concern. It's just like my main thought on the matter is like, how do we know that what is being specified in TLA plus is exactly the thing that's being implemented in the Scala code, right? And I guess that's sort of the snag all the time, is like you're writing this high level model of the design in TLA plus, and you can check that like your design is good, but then how do we know that somewhere deeper down in the implementation there aren't bugs or something? But you know, like of course it, like TLA plus is not going to catch all of the bugs. It's for the design. So yeah, I don't know.
For this part,
The sense that I'm getting from this is that you could define types in Scala that essentially correspond to the TLA specification, and the type definitions themselves could become proofs. I guess you know, I'm extrapolating this way too far, but it seemed like he was saying a little more than that. The traits being defined there were have a behavioral component to what they're describing. You know.
So.
Not really.
Yeah, this is maybe too complicated, or what I was thinking is just to somehow translate these transitions in one trait.
Yeah.
So we can be sure that implementation is correct. Sorry.
So the TLA would specify how these things could combine.
Yeah.
You know,
it's kind of
this can be
like. Yeah, go ahead.
Yeah, sure, please.
Oh, no, I was just gonna say like TLA plus is just like, you know, saying like, given that you're starting in some specified state, and these are all of the allowable transitions and all of their enabling conditions and everything like that. It's just like saying it depends on what you're testing, right? If you're doing like a safety test, it will tell you all of the possible behaviors basically and test all those possible behaviors. And then if you're doing a liveness test, it'll also look to see if some temporal conditions hold for these possible states that you're kind of constraining the system to obey by.
Yeah. So we don't have, in this situation, we don't have proof in Scala. We just we just know that we can call, for example, save, and after that we can call find email, and this is fine. But if we don't call save before that, it is not okay. So this can be generated from TLA directly. So we can say, oh, our Scala code is definitely in lockstep with TLA.
And
we don't have proof. We don't have proof in Scala. We're just saying, okay, you know, we are the code is generated. So
I think this is a really cool idea, and we should definitely talk about this more. I like this, and I would like to go over this in more detail with you, Tomislav, because I would like to understand. Absolutely. So I guess what I'm saying is maybe we can kind of like postpone the rest of the conversation about this discipline stuff for right now, and we'll figure out a time to talk about that, and then say the stuff about TLA plus.
I just wanted to say that you have some in your mind that you have this notion of, you know, recognizing transitions as something that can be translated to Scala. So, you know.
Exactly.
When writing TLA, maybe you can
and so I mean, I was thinking that you know, and I think I said this last time about how, like, you know, when you start thinking a lot about one tool, every problem starts to look like you can solve it with that tool. And so I wanted to like pose that to all of the devs and see if I was making that, like, if that was just a fallacy of like looking at the same tool too long, or if there was maybe actually something to it. And I think from Martin's answer, it sounds like there's something to it, but it might be really complicated, I guess, is what I got from him.
Well, you know, it would seem to me that, you know, what would be useful is if we could, you know, annotate, you know, Scala or row line to constrain the specification, or to type the row line, you know, which is untyped right now. You know, how could we do some kind of annotation that would add a type system to row line?
That's interesting, because I started right before Ralph started to push me to look, you know, like mostly really just focus all my time and energy on TLA plus stuff. I had started working on some sort of like type inferencing function for Rolang. And the types that I was using are like spatial types, which are really just like the patterns that you use in Rolang. And basically my thought was that the original way that I wanted to approach the tuple space and comms with multi-listen receives wasn't going to work out, because I couldn't use the you know, bags or multi-sets or whatever you want to call them in at least from the configuration in K-framework the way that I thought I should be able to use them. And so that started to make me think about a different way to structure that stuff. And so I basically started to instead of just storing sends and receives as elements in a multi-set, I started to like type them a little bit. And so what I mean by that is I actually stored them in a structured set, and the elements in, say, like, for example, for a send, what are the important things about a send? The important things about a send are the channel that they're being sent on, and that's like the explicit channel. So I don't need to type that. How many messages, so channel they're being sent on, like explicit name they're being sent on. The type of message that's being sent, and the reason that it's the type of message that's important, not the actual message itself, is because that's where the pattern matching works. It works on the types. And so basically I was thinking like, if I can group all of the sends on some specific channel that have the same type, like, so for example, you know, I'm sending on the channel at 0, you know, like the integers 0, 1, 2, 3, 4, 5, you know, whatever. I have 6 messages there. They all will match with the same receive. And so really the only important information there is the fact that I'm sending an integer, right? It doesn't matter what integer yet, I guess, until you take into consideration like guards and that sort of stuff, because then maybe you can say like, oh, well, I want an integer, but it has to be greater than 2 or something, you know? And so I started to structure the collection of sends in terms of like what, you know, I was calling it basically like namespace, but it's really just like the channel that is being sent on. And then like within the channel kind of, I don't even know how to say it. So like the set element, so there's like an outer set and then there's like inner sets. And so the outer set is first specified by like the elements of the outer set are first specified by like the channel that the messages are being sent on. And then there's another set that's associated with that channel. That set is basically like what type of messages is being, you know, are being sent on this channel. And so like, you know, if I'm sending integers, if I'm sending bool, you know, those are going to split into like 2 different elements of that kind of inner set. And then, so like in my example, you know, I had several integers. And so like each one of those integers will be an element within like another further inner set, if that makes sense. So there's kind of like almost like indices for the sets, and they're nested sets. I don't know if that makes sense. It's really hard to explain without showing it.
I would think the types would be constraints on
yeah. And so the moral of the story, right? This is like TLDR or whatever, but so more of the story is once I started to structure the sends in that way, then I was basically like, oh, well, that doesn't get me anything unless I know what types of messages a receive is expecting, or really just a bind in a receive. Like I need to know what types for the variables it's expecting. And so basically then that leads me to say something along the lines of like, okay, if I have a receive with, you know, however many binds, it doesn't matter, it could be 1 or multiple. I need to then look at each one of the variables that appears in each one of those binds and then try to constrain the allowable types for each one of those variables. And so like, for example, you know, if I don't specify in my receive, I'm just like listening on, you know, the channel at 0 for some variable, which I'm calling X, but then I'm going to add this variable X to like the integer 5 or something like that. I know that I'm expecting X to be an integer, right? So I can take that like X plus 5 in the continuation and then kind of pull back from that and say like, I know this variable needs to be an integer. And so that's what my function was doing. Basically, it was taking a receive like that and then saying like, okay, like these are the variables appearing in your binds, like how do I type each one of these variables? And I look to the continuation to do all of that stuff. So like from the continuation, I can then say like, you know, X has to have this type and, you know, whatever. And so then in a comm event, when I'm looking at that particular receive, it will know like what portion of these like nested sets in this like send thing to look for. I don't know if that makes any sense, but basically then what I was thinking is like, I could just have it choose like a random element from the right part of the send set, if that makes any sense.
Yeah. I mean, I think I grasped the you know the basic part.
Yeah.
So you have this notion of inference from continuation, right?
Yeah.
Which looks cool, right? To
Yeah.
have.
Yeah, and you know, like I said, this is something that I started working on right when I was kind of asked to change my focus a little bit. So I definitely didn't finish it by any means. But I feel like I had made enough positive progress to give me hope that something like this can be done, if that makes sense.
Cool. Yeah, that's cool.
So the applying the TLA plus to Rolang is we don't really have a clear path there.
Yeah, right. Yeah, so those are two kind of like disjoint things in my mind currently. I'm not sure how one could influence the other at the moment.
All right, well, thanks.
Yeah, absolutely. Okay, I should probably start showing some TLA plus stuff. I have like a super basic example, but like I was saying in Discord, I think that this is a great example because it's really simple, but it shows like some good features of TLA plus. So let me share my screen here. Oh, cool! I can just make it go right to that. Nice. Okay, so the setup for this system is basically like we're trying to track the value of a clock. So we're trying to model a clock. This clock can only have one of two values. It's either 0 or 1, and so that's why I'm calling it bit clock. This is like directly from the TLA plus article on Wikipedia. The TLA plus article on Wikipedia is actually really good. So highly suggest reading that if you're interested. So like I said, we're trying to model a clock, and so there's only one variable. That variable is called clock, and basically what it's going to do is just take either the value 0 or 1, and the only allowable transitions are going to be it changes from 0 to 1 or it changes from 1 to 0. That's basically it. And so we'll go through all of this stuff, but essentially what we're saying is to initialize it, we're just going to choose kind of arbitrarily, that the value of this variable is either in 0 or 1. Of course, like we want it to always be a value 0 or 1. So initially we just take it to be one of them, and it doesn't really matter which one. I added this extra thing here just because this is, I guess, something that I'm trying to get into the habit of doing, which is basically just like a type check for the states, just to make sure that the variables that I'm defining take the values that I want them to take, basically, right? And so like the only condition, yeah, go ahead.
I mean, this is valid for all transitions.
Yeah, so this is a state formula, or a state predicate specifically because it's a state formula that's Boolean valued. And so in general, you can have state formulas, you can have action formulas, and so these two things are state formulas technically. Well, okay, maybe this might not be so correct because I'm not using it in the way that I want to test it in every single state. Type OK, I am using it as a state predicate, and I want to test that it's true in every single state of the behavior. So that's basically it. So this is just the initial state, right? Like, the clock variable has either the value 0 or 1. Cool. And this is like, I'm going to check in every single state that the clock variable has value 0 or 1. And that's really all I care about.
And you can specify multiple this kind of types.
Yeah, definitely. Yeah, like any state predicate you want, you can specify to check that in the model checker. And I'll show you how to make sure that it is actually checking that type OK is satisfied in every single state, and we'll get to that in a couple minutes.
So can I just ask? So in this specification, this type OK doesn't do anything, right? But when you create a model, then you say, oh, this is my this is something that I want to check and be sure that.
Yes, exactly. Yeah. That's a good point that you just made because so init does something tick does something, spec does something. Type OK doesn't really do anything. It's just kind of like a formula that I want to check in any model that I generate that it is satisfied in every state. So basically the point is, just like you said, this isn't really doing anything for the specification. It's just going to check properties of the specification later on. I don't know why I spaced so much there. I see. Either way, so the only transition here is this transition called tick, and basically what it's going to do is say if the clock variable has a value 0, well then in the next state it's going to take the value 1. That's what the prime means, right? So like clock is current value of the variable. Clock prime is like any transition, according to tick, right? Any next state, this is a new value of that variable, right? So if it was 0, now it's 1. But if it wasn't 0, well, it had to be 1. And so if it's 1, then it'll change to 0, right? So this is like the value actually changes if this tick transition ever occurs, right? Because remember, something about TLA plus is that the transitions that you define never have to happen because it is an admissible behavior to have all stuttering steps. And again, by a stuttering step, I mean that the variables that I care about, like clock in this case, if clock does not change value, that's a stuttering step in this particular specification. And so I should have waited to say that, but I'll say it again in 1 second, because basically the only thing left to talk about here is the spec definition, right? And so this spec is like a special kind of formula that I write. And so I'm basically saying to the TLC model checker that what I want to happen here is start in the initial state init, right? Check that this predicate is satisfied. And then for all states that come afterwards, basically the only way to get there is to do a tick. Or remember, there's like this underscore and then the variable. So it's like you can get there by a tick, or you can get there by not changing this variable, which I specified here, which is clock, right? So essentially this means that the only possible transitions are going to come from tick or a stuttering step.
So if you change the tick, so in a way that doesn't change the clock. So for example, you can say that in both cases the next clock will be 0.
Oh,
what
yeah, you mean like that?
Yeah.
Or yeah. Okay, so yeah, so changing the definition of the tick transition, like regardless of if clock is 0 or 1, it's going to change to 0 no matter what. Okay, so sorry, what's the question now? Yeah,
I'm just wondering where will be the problem detected, or are we going to see some unexpected or?
Well, so go ahead and generate a model. Okay, so something we talked about last time is that so there are different ways to specify what the behavioral specification is. So one way you can do it is by saying specifically what is the initial state, what are the next transitions, basically. Or you can do it just by supplying some temporal formula, which is what I did with Spec, right? If you call it Spec, it'll automatically come up in this state, like, oh, I know you want to use this Spec formula that you wrote as a temporal formula to specify the behavior. Or you can just say no behavior Spec, right? And then it's just like all allowable behaviors. But we want this one. I'm not sure that we want to check for deadlocks, but I'll just leave that on. We did want to check, and it should be pretty obvious that this is not going to be violated, but we'll go ahead and just check type OK in every state as well. Right, because basically what we said is like, it's going to start with a value of either 0 or 1, and the only allowable transitions are the value doesn't change or the value changes to 0. Right?
Mm.
So we can go ahead.
So this will work, right?
Yeah, yeah, it should. I don't expect anything bad to happen here. Yeah, so it works out just fine. Didn't find any errors, but then again, we're not saying a whole lot, right? We're just saying the only thing that we care about is that it starts in that initial value, either 0 or 1, and that the only allowable transitions are to not change that value or to change that value to 0 if it's, yeah, or to change the value to 0, that's it.
Yeah.
Right.
Yeah. We are not saying,
yeah,
so we can see this tick as, as a specification, right? Where a tick is really saying, in each tick, the value will be changed. And this is the specification of tick, right? So we really change the specification, right?
Yeah. So tick has an enabling condition. Well, it's not really. There's not really a whole lot of enabling condition here because it's like an if statement, right? So it's either this is true or this is false. That's the enabling condition, and depending on whether it's true or false, we get these two possible behaviors, which change to be exactly the same thing. So basically what I was saying here is like there's an implicit enabling condition. And so by enabling condition, I mean like some predicate that is satisfied so that this tick transition can happen or step or whatever. Right, so there's some condition that must be satisfied for this thing to ever even be possible to occur. The thing that has to be satisfied is clock has to have the value either 0 or not 0, and there's only two cases, it's either 0 or it's 1, right? And so basically I was saying here, there's like an implicit enabling condition, and that enabling condition is it's either 0 or it's 1, and that's basically it. But those are always satisfied, right? So tick is always enabled, I guess, is the thing.
Okay.
Yeah. So I'm going to change this back so that we actually are saying whichever value it has, tick will actually change the value and not just keep it as the value 0 if it's at 0. Okay, that's it. That's it from this original model that we just did. Okay, does that make sense? Do you have any questions or anything about that?
Yeah, I'm looking at these results, and what will be different is the something in the state, right? I mean the number of detected states.
Yeah. So I think that it's going to be the same, if I remember correctly. Something here might change, because it says it found states in 2 states for the init action and the tick action. I'll be honest, I'm not 100% sure what this means. So what I think it means is that this init action can be satisfied in 2 possible states, I guess, and this tick action be satisfied in 2 possible states. I think that's what it means. I'm not 100% sure. The fact that these 2 are distinct is pretty clear, right? I mean, like, either clock has the value 0 or has the value 1. Those are 2 distinct states. Here, I think it's saying 0 distinct states because we already saw both of those states here in the init. I'm not sure, but that's the way I'm kind of interpreting this. I don't know if that makes sense. And then
and also depends what is the initial state, right? 0 or 1.
Yeah. Yeah.
Because tick will do something or not. Okay.
Yeah. Yeah, and so there's some other information over here, like how long did it take to find these states, and how far away from the initial state you got. And then, you know, same kind of states found type of thing. I don't really know what this Q size business is all about, but it looks a little bit weird somehow. Oh, maybe, okay, I think these higher ones are adding with the lower ones. So like, I think at diameter 1, it found 2 more states, and so it added the 2 and the 2 together to get 4. And so I think here, since there were 0 distinct states introduced by by tick, this is still 2 distinct states. But I don't know what the Q size is.
Okay, cool.
Yeah. Okay, and then I also don't really know what this fingerprint collision probability thing is about, but as long as that shows up, we're doing okay. Yeah, all right, so that's it for that. I think I had.
Okay. Can you execute this model?
Yeah, so I'll run it now with the kind of, I guess, like appropriate things here, and so I have it here, I believe.
Okay.
Variance. Hold on, I need to make that smaller. I don't remember if I put everything in here. Yeah, weird. Strange. Yeah, all right. So yeah, we'll just look at this. So I mean, so it's always waiting for me to you know, run TLC to actually run it on the specification that I have here. So now that I've changed it and saved it, it's good. It'll run a model on this specification. So again, we have, you know, spec. One thing I didn't mention before was this deadlock stuff. Like, do you know, want to check for deadlocks? And so a deadlock is basically just getting to a state that you can't transition out of. But any state that we enter, we can transition out of it because tick is always enabled. So there won't be any deadlocks. I might as well not even check for them. And then the other thing is that I still just want to get into the habit of making sure that typo K is always true, right? And so this basically is saying, like, check this typo K formula that it's true in every reachable state, right? So every state that you encounter, like, check that this predicate is satisfied. And then, yeah, I don't really need that right now. Okay, so then we'll run the model checker on that. And so basically get the same kind of results. Like, we only ever get one step of, you know, away from the initial state that we started in. Same number of states found in distinct states and all of that stuff. But again, it seems pretty obvious. Like, distinct states is like, well, either clock is 0 or 1. You know, like, those are the 2 states. That's it. Yeah, so that's basically all that's going on here. And so we didn't find out a whole lot of information here. We basically just found out that this is not a totally crap spec for this thing. But, you know, then I posed some questions here, like, well, but is this really useful? You know, does it actually have, like, the desired behavior that we want? Because, you know, is it an allowable behavior for this clock to never change value? And so basically, you know, kind of what I'm getting at is, like, does this really do what you want it to? Like, you know, what's the use of a clock that is allowed to never change value? You know, if you want something that's sort of like keeping time in terms of, like, it, you know, changes value, right?
Yeah, you want the tick always change the state, right?
Yeah, you always want it to be possible to change the value at the very least, right? And so basically the point is that it is possible, given this specification, for this clock to never change its initial value. And the reason that that's possible is because we're specifying here that the allowable transitions are tick or don't change the value of clock, right? Do a stuttering step, basically. And so an allowable behavior by this spec is, well, and any spec is always just do all stuttering steps. But the problem is, well, that doesn't really give us a useful model of this clock, right? Because now we're allowing it to just like take the initial value 0 and then never change it. Like, what's the point of that? So then the goal is to like get rid of that. And so basically what I would like to do at this point is introduce some more things essentially. And so what I want to do is make it so that I can say something about, so there's this predicate that I'm going to define here, and it says it down here, and I'll kind of explain what this means. Basically, I want to somehow make a condition that I can check that's basically like this clock ticks at some point in time, right? And so the initial problem here is that given this spec, that was not necessarily the case, right? It was possible there were allowable behaviors that that wasn't true. And so now the question is like, well, how do we change that, right? Like, what do we do? What do we introduce? What do we change to make that not the case anymore? And so my idea was to add another variable, which I call init clock. And basically what init clock is going to do is, so let me, I can keep all of those. I just need to specify this as the initial state. So init clock,
in a sense,
yeah.
In a sense, you're adding liveness, right? This is something that you want to model.
Yeah, exactly. So in a sense, I'm adding some way to check that the clock eventually ticks.
Okay.
And so yeah, that's like a liveness condition, right? And so basically the point is, what I'm doing is ultimately I want to add this condition that I call clock eventually ticks, and it's some temporal formula, right? It's like a diamond of this condition, and I'll explain all things. So it's a diamond of this predicate that's like clock does not equal init clock. And so I never explained this, but maybe it's already obvious. Like, again, clock is still just some value in 0 and 1. And then init clock is just going to be assigned the value, whatever initial value clock took, that's the value that init clock gets initially. And then basically the idea is init clock never changes. It always stays at the same value. And so at any later point in time, I can always check if the clock value, how it compares to the init clock value, if that makes sense.
Okay.
Right, because before there was no way for me to say like, oh, how can I tell if the value has changed, basically, just because there was nothing that preserved the initial value of the clock or anything like that.
Okay, so you're saying you will take init clock variable, you will fill init clock variable only once.
Mm-hmm. Yeah, and so how am I saying that? So here, this initial state formula is basically saying clock gets a value in 0, 1. Init clock takes the value of clock. And then the transitions that I'm going to consider are going to be the same exact one from above, like, you know, if clock is the value 0, then change it to 1. If clock has the value 1, then change it to 0. And also, do not change the value of init clock ever. Like a tick, you know, I'm calling it e-tick here. E-tick never changes the value of init clock. It always remains the same. And then specifically what I'm going to do with the specification, right, this e-spec formula, it's going to initialize in, you know, this e-init initial state. And all of the transitions that I'm allowing, so the way that I'm reading this, right, is like all of the transitions I'm allowing are either going to be an e-tick transition, which doesn't change the init clock variable, or they're going to be transitions that change neither of these variables, so they won't change init clock and it won't change clock. Right, so it's a stuttering step, basically. Like now I care about the value of 2 variables. I care about clock and I care about init clock. And I don't want, and So a stuttering step for me now is neither of those variables changes values.
I'm not sure. Why are you specifying? So you're saying, okay, this can be init value, or it can be, I'm not sure that I can read eSpec. Init,
yeah.
You must do init or, right?
Yeah. So einit just tells me the initial state that the system is in, right? And so the initial state is clock has some value, either 0 or 1, and init clock has the same value.
But you have this AND operator between init and in the right hand side. So why is init? Do we know that init will happen before etic?
Yeah. So what I'm going to do is when we come over here to like what's the behavioral spec, I'll tell it to okay, one of two ways, right? Either I can specifically say like, hey, the initial state is init now, and the next state, well, is etic. I'm not sure this is exactly how I want to do it. I know for sure the way that I want to do it is say temporal formula and make it eSpec now, right? And so basically what that tells the model checker is like the initial state will be this init state, and then your allowable transitions are coming from either an etic transition, which is defined here, or they're a stuttering step. And by stuttering step, I mean it changes neither the clock or the init clock values. Okay. So that's basically it, right? And so then the question is basically like, okay, now given all of this stuff, right? Like we introduced this auxiliary variable, which basically just like stores the initial value of the clock, and we've refined the transition. We've refined the spec. Like, did we do enough? And so my claim is that definition of doing enough means that we satisfy this clock eventually ticks formula. So what are your thoughts on that? Do you think this?
So I'm thinking that you only set init clock once. So how can you detect the clock will change? So in one change, init clock will be the same as the clock, right? And in another change, it will be different, right?
Yeah.
So how do you check?
So
change?
What this formula is saying is like true will mean that at some point in time, right? That's what the diamond tells us. Eventually, at some point in time, in some state, in a behavior, this formula is true. Clock does not equal init clock. And the reason that's interesting is because initially we set it up so that they have the same value, right? So it's interesting whether or not this formula is satisfied, because that means something interesting happened, right? Like the value of clock actually changed.
Oh, you're not saying the clock will continue changing, 0, 1, 0, 1, 0, 1. You're just saying from the start it will change, right?
Yes.
And that's it.
Yes.
Okay, this makes sense.
Yeah. So we don't have that aspect yet.
Okay.
I'll introduce it in a second, but we don't have that aspect yet. Okay. So then the question is, does this spec that I now have satisfy this predicate?
Yeah.
It does. Okay. Yeah. So let's check it. Okay, I'll save. This is good. So what I need to do is make eSpec the behavioral specification, and I want to check this as like a property of the behavior. So I made eSpec what it needs to be. Type OK. I always want to check properties, temporal, true for every possible behavior. Don't think that's what I want. I want additional definition, state constraint, restricting possible states by state. Yeah, hold on a second. Model values.
So you're looking different.
Yeah, this is what I want. Yeah. So I
you
want
have different.
Right. So what I want to do now is run the TLC model checker with this new eSpec behavioral specification. This is not super important, this type OK thing. I'm just going to hide that now because it's really just not that important. But the new thing that we introduced is, well, different behavioral specification. And also, I want to check that this temporal formula is true for every possible behavior.
Can you explain what is the difference between this another checking of type OK? This is for every transition.
So type OK just checks that the value of the clock variable is either 0 or 1 in every state of the behavior. Right. So this is kind of just saying, like, you know.
I mean, my question is, why didn't you enter clock eventually ticks in the same box with type OK?
Oh, yeah. So because this doesn't take a temporal formula, right? Because we're asking for a state formula here. We're asking for something that's true in particular states, but this accepts temporal formulas, which we want to hold true for every behavior. So behaviors are like sequences of states and steps, basically. But these invariants are like in a given state, you can check that this thing is satisfied or not.
Okay, this makes sense.
Okay,
thanks.
Makes sense. Cool. Yeah, and like I was saying, basically, that's not super important right now, so I'm just gonna hide it. The thing that we wanted to see is whether or not this clock eventually ticks thing is satisfied. So let me save this and then go ahead and run it. Okay, so generated counterexample. So it's not satisfied. So it says here, you know, temporal properties were violated. It's a little bit weird that it doesn't tell me which temporal property, but I guess maybe it's obvious because I only have one. But it even gives me a counterexample, which is really cool. So basically what this is saying is we're going to start with an initial state. And so, for example, like both values are 0. And then every transition after that is a stuttering step. So what that means is we're going to start in some given random state, like it could have been 1, 1, or it could have been 0, 0. And then every other transition out of that state just doesn't change those variables.
But tick should change the clock, right?
Yeah, but remember the whoops, that was the wrong thing. Remember, so this transition applies. So the allowable transitions are an e-tick, which will change the clock variable, or a stuttering step. And by a stuttering step, I mean it doesn't change either of these variables, right? So basically the whole point is, like, we can initialize it in some state, 1, 1 or 0, 0, and it chose 0, 0 here. And then an allowable behavior by the specification is to not change either of the variables of concern, i.e. to do stuttering steps, right? So by this specification that we've written here, this is an allowable behavior to start in 0, 0 and then just continue in that state forever, basically.
Oh, I see. It's almost the same as previous example, right?
Yeah, exactly.
But now you have a tuple. Okay.
Exactly. It's I would say even more than almost the same. basically identical to the previous situation,
Okay,
right?
yeah.
Like we didn't do a whole
Yeah.
lot. We just introduced this new variable that told me like, hey, I know the value at the beginning, but that's it, you know? So how I can't ever say that it will change values if I'm allowing for this infinite string of not changing values, basically. Okay, whoops. Cool, that makes sense.
Yeah, so you need to delete this, right?
So
and only allow etic.
So that is not allowable in TLA plus. And basically the reasoning is because we care about the value of these variables, but we're thinking of our specification as like a piece of a system that has more moving parts than we possibly even want to monitor. So we have to allow for state transitions that just don't change these values. So we can always think of every single spec in TLA plus as like just this little piece of a system that is a part of like a whole universe, which, you know, is always the case no matter what you're doing. And like things can be going on in the universe that you have no control over and also, quite frankly, don't really care about. And you only care about these values and you just want to say things for behaviors that, you know, affect these values. Kind of. Yeah.
So can you just say that init clock will not change without specifying clock?
Without sorry, ask that again.
Can you just specify init clock without the tuple with the clock?
Yeah. So I mean, I could have originally just said, you know, init clock is a constant, and then just given it the value 0 or given it the value 1 or something.
I was thinking, can you specify? But I was thinking that without changing anything, how you set the value? Can you just say that in this line that you have selected? Can you just say without specifying a tuple? Can you just say init clock?
Oh,
it does not change, or this is also not allowed.
Can I just say init clock? I'll have to think about that. So you're saying, can I just like do that?
Yeah.
Okay. Let's see if it likes it.
Does this make sense or?
Yeah. So what we're saying here is like the allowable transitions are a change. Oh, actually, I don't think this makes sense, but we'll see. So the allowable transitions are given by etic here, which changes clock to either a 1 or a 0, depending on if it's a 0 or a 1, and it doesn't change init clock. And we're saying we're allowing any other step that solely does not change init clock. I can already think of a counterexample, and that counterexample is regardless of the value of clock, I change the value of clock to 2, and now it doesn't even satisfy type OK. So let's see what happens when I run the model checker on this now. We don't even really care about that. I do care about type OK. Let's see what happens now.
So you're saying someone else can change?
Yeah.
Someone else can change the clock.
Yeah, and I know it's really small and I can't change the size, which is unfortunate, but or I don't know how to at least. Basically what it's saying is the next state relation specified by the spec doesn't contain the state variable clock. And so that's just not even allowed for the model checker. So I have to say all of the variables here can't change in a stuttering step. So I'm gonna go ahead and not do that. Okay. Yeah, so it doesn't even allow it. It parses it, but it doesn't allow it for the model checker. But like I said, you know, even if it did, I provided one of infinitely many counterexamples that would not even obey type OK.
I see. Okay.
Yeah. So, okay, so this wasn't enough to get this satisfied. Can we do something else? And basically the thinking is like, so we're saying somehow we want to impose some sort of liveness condition, right? This is checking that the liveness condition is kind of satisfied. But like, what is the liveness condition is kind of the question, right? And so there are these two notions of weak fairness and strong fairness. These are both like liveness conditions. And weak fairness basically says that if a transition is always enabled, so like in the case of this ETIC transition, like the enabling condition is, you know, this is true or this is false, right? Because then the if can proceed. So the enabling condition for ETIC is like clock either equals 0 or clock equals 1, right? And so it's always enabled. In any state, it's always enabled because clock can only take the value 0 or 1, and we're checking that every single time, right? We're checking that typo K is satisfied. We know this is always the case. So basically, point is ETIC is always enabled. And so then, since ETIC is always enabled, what weak fairness is going to tell us, if I say like I want to impose weak fairness on the ETIC transition, what it's going to say is if the ETIC transition is always enabled, which it is, then an ETIC step must happen. Okay. Strong fairness is a little bit different, and strong fairness basically says that if a transition, so strong fairness of a particular transition, which I'll just call ETIC here because, you know, that's what we're talking about. So if ETIC is repeatedly enabled, that means like it may be true and then some transition happens and then maybe it's in a state where it's false, but then some transition happens and then it's a state where it's true again, and et cetera, right? If it keeps coming back to the fact that it is enabled, strong fairness is going to say that an ETIC step must happen, even in that case. So weak fairness was like always enabled, then it must happen. Strong fairness is like repeatedly enabled, then it must happen. So it's a little bit stronger. Strong fairness is a, you know, a stronger condition, obviously. You
okay,
need to, yeah.
Can you just, I'm not sure that I'm grasping this enabling condition.
Yeah, sure. So enabling condition, yeah, go ahead.
I mean, what does it mean when you say ETIC is enabled? And and TIC also. You said that TIC also is enabled.
Yeah. So it would probably be more clear in a different situation. But so what it means for this transition to be enabled is like, so with a transition, you can specify some sort of state predicate. So like you give me a particular state of the system, and I can apply this formula to that state and return a true or a false value. If that value is true, then we say that the transition is enabled. And so in this case, the enabling transition here, and it's a little bit weird, right? Because it's like, if something, then something else something, the enabling condition for us here is if one of these branches fires, basically, right? Like, but that's going to happen in either case if clock is equal to 0 or if clock is equal to 1, right? Because if then else works if the predicate is you know, if this expression is true or false.
So if not enabling condition would be if you only react to 0 or 1, but not the both.
So an example of a state predicate that is not an enabling condition for ETIC would be like init clock equals 2. Like, I don't care what the value of init clock is. It has nothing to do with this transition whatsoever. Only the value of clock has something to do with whether or not this transition happens.
Okay.
Does that make sense?
Is this
So
related to
like,
how do you look at the whole state that you are manipulating?
Yeah. So the state is just an assignment to variables, right? And so the only two variables that I care about are clock and init clock, right? So a state is just going to be an assignment of values to those two variables for me. There are a bunch of other variables, and that's what like the stuttering step business is about. But I literally don't care what any of the values of those variables are. I only care about these two variables. I'm only caring about this like tiny little portion of the universe.
Okay.
Yeah. So, okay, just as an example, right? Like something I could also say here that would be an additional enabling condition would be like, for whatever reason, I really need the value of init clock to be equal to 0 in this case. Right, and so basically what this is going to say is like, e-tick is only like, it's only possible that this e-tick step will happen if I have both init clock equal to 0, well, and clock is whatever value, so that doesn't it's not really that much of an enabling condition because it's always enabled. So in this case, it's like this e-tick step will happen if and only if init clock is equal to 0. So it'd be like another example of an enabling condition, I guess. Yeah.
I see.
Yeah.
Okay.
Okay, cool. I'm gonna get rid of that. Ooh, that's not what I wanted. What am I doing? There we go. Okay. Yeah, so that's basically it with this discussion, I guess. And so like I was suggesting, the thing that needs to be done to have this temporal formula satisfied is we need to impose weak fairness, or some kind of fairness, but weak fairness is good enough. Because in this case, weak and strong fairness are equivalent, because this transition is always enabled. But okay, so either way, that's kind of the solution, is we require weak fairness of, well, tick or e-tick or, whatever, doesn't really matter. I guess e-tick is really the right thing to say here. Oh, I see what I did. I got rid of, yeah, okay, so point being, the only reason I ever introduced this init clock variable was to specify that this thing happened, kind of, right? Or to see if it happened, right? But I don't need this variable really for anything. The whole point was just to generate a discussion about how can I tell if this original specification is even useful, right? And there was no way for me to do that other than to produce this auxiliary variable and then check the value of the original variable against the auxiliary variable, I guess.
Okay.
And so, so what I would like to do then, and actually I will do it with e-tick here. So let me do this and this and this, and then weak fairness. I think I need to do, yeah, I think I need to change both of these to init clock as well. I don't know if that's the right notation for that, but we're going to find out in 1 second.
So WF is weak fairness.
Weak fairness, yeah.
So this is something integrated in TLA that you can just impose on some variables.
Yeah, which is really cool. Yeah, so like weak fairness and strong fairness are two like really powerful things that you can utilize in TLA+.
Okay, I see already that generate the code for this is probably not easy.
Yeah, right. Yeah, good. Cool.
Okay.
I'm glad you're getting some insights about that. All right, so let's see if this works now. I want to say originally I'd run it with yeah, actually I don't know what I did originally, but we're gonna change some stuff here. So I want to check that condition. Still checking type. Okay, not that it really matters. And now I'm checking spec correct, I think is what I called it. Let me see if that's what it was. Yeah, spec correct. Yeah, so okay, so this all looks horrible now, but basically what it's saying is we're going to start in this init state, right? It's basically just assigns some value 0 or 1 to clock, and assigns whatever that value was, the same value to init clock. The allowable next states, allowable next transitions are given by the ETIC transition or stuttering steps that don't change either of these variable values. And we also have imposed this weak fairness condition on this, you know, okay, there's really only one transition here anyways, but we've imposed it on this, this transition ETIC, right? And basically we've said weak fairness of ETIC means that if ETIC is enabled continuously, then it has to apply at some point in time. Which basically is just saying that this formula better be satisfied. So let's see if it is. So we got this, correct spec. Yeah, I think we're good. Let's run it, see what happens. We did it. It's a little bit,
oh, now distinct states are 2.
Yeah, so it's a little bit disappointing because it doesn't give you any kind of like victory message or anything. It only tells you when you're wrong. It doesn't tell you when you're right. It's a little bit unfortunate, I guess. But the point being is, you know, we've specified to check this temporal property of clock eventually ticks, and it passed. It did check out that we had this clock eventually ticking. Right, and so to say that just one more thing, to say that the clock eventually ticks is to say that it will always eventually tick another time. Again, because that weak fairness applies when you have continuously enabled that ETIC transition, but ETIC transition is always enabled regardless of the value of clock and init clock. And so it starts off in a state where it's continuously enabled, so it must transition using ETIC. Once it transitions using ETIC, you can basically just like recursively apply that same logic, right? Like, okay, now we're in a state where from that state, it's, you know, always enabled, so it must be enabled, you know, it must apply again, and then et cetera, et cetera.
Again, yeah.
So it will tick indefinitely.
Cool.
Yeah.
That's cool.
Yeah.
Can you go to specification?
Yep.
And
yeah, go back here.
I'm still seeing the model.
Here.
I think it's slow. My Zoom is slow, probably.
Oh.
Okay, now I see.
Okay.
But yeah, can you go to a specification?
Yep.
Okay, so in the spec, correct? The second expression is you said that the next state, yeah, can be ETIC or not changing clock and init clock.
Yeah.
But because of weak fairness, this will never happen, right?
So it will only happen for a finite amount of steps. So okay, so we're saying we can either have an ETIC step, or we can have a stuttering step. And by stuttering step, we mean don't change clock, don't change init clock. But weak fairness is imposing that if we take these stuttering steps, you know, just keep taking stuttering steps, there has to be some point in the future where we actually take an ETIC step, because that ETIC transition is always enabled in every single state.
Oh, so you are saying ETIC is this transition, but maybe something is in between, right?
Yeah,
which will reflect as clock, and init clock is not changed, right? Because something else is changing, so we don't care. But eventually, ETIC will happen again, and this will be the enabling condition that that will produce this change.
Yeah, so like, you know, as a totally ridiculous example, like, you know, we start in the initial state. There can be 10 billion, you know, stuttering steps, but throughout every single state touched along that 10 billion step sequence, this condition, this ETIC transition was enabled. And by weak fairness, at some point in time, we have to have an ETIC transition actually happen. So let's say we go 10 billion stuttering steps, it was enabled the entire time. We have to have one happen. And let's say now it happens. But now we're basically back at the beginning, because we're saying, okay, we have some state that we're now in. It doesn't matter how many previous states there were. We're now in some state that enables this ETIC. We can have any amount of stuttering steps in between, any finite number of stuttering steps. But again, ETIC is enabled the entire time, so it has to happen again. And so it will.
I see. And in all of these staggering steps, the clock init clock will not change.
Yeah, exactly. That's the definition of a stuttering step. Yeah.
Cool. I think now I better understand how you specify this kind of behavior.
Yeah, and it's funny, right? Because like, how much do we really talk about? Boy, there's only 37 lines of code here, and half of it is comments, you know. And you know, so like I'm saying, like, this is a very simple system that we're modeling here. But even still, it brings up some relatively complicated ideas, because there's like all of this stuff about like behaviors and enabling conditions, and, you know, weak fairness, and you know, like temporal conditions, and just all of this stuff. So I thought this was like a really cool example.
Yeah, definitely. And very, very good explains how you just add for example, fairness is just additional. I'm not sure if constraint is good word, but you don't have to change how ETIC works. You're just saying, and additionally, I want this property. And
right. Yeah, just like, you know, can join this weak fairness property on there, like done. You know.
Because I didn't see how can you do this without changing ETIC, right? Because you said, okay, it can be ETIC and can be the same state. What? I mean.
Well, yeah, and so and my claim, and I don't have a proof for this or anything, but my claim is there is no change you can do to ETIC to get this same result out of it, right? Like, this is an inherently more like expressive or powerful condition that we've used here, or tool, or whatever. And so I don't even think there is something that can be changed about ETIC to impose something similar, like weak fairness.
Okay, I see.
Yeah, because we don't have any information about, so when we're in a particular state, we don't have any information about previous states. We only know the and how we can transition out of that state. And so that's kind of like my heuristic argument for why I don't think it's possible. But I don't know if that's actually true. That was just kind of my intuition that it shouldn't be possible. Yeah, but you know, that's why weak fairness is so powerful, because it allows you to say something like that.
I mean, you can track what is the previous state, right? You can have a variable previous clock, but this doesn't mean that you will have a way to impose fairness, right? It just means that you know previous value, but
so
right?
And yeah, and with that there's still an issue, because previous clock is now a variable, so stuttering steps don't change the value of previous clock. So how many states have we gone through before the one that we're currently in that didn't, you know, do anything with the previous clock? But I guess, you know, previous clock is always going to have the same value if it's not changed. So I don't know, that, you know, doing something like that might be a good way to go. But and the fact of the matter is, like, now that I know this works, I can just go ahead and get rid of this condition. I don't care about it. I can get rid of all of this other stuff with this auxiliary variable. I don't need it. Oh, actually, I didn't need to do that. But I don't need this auxiliary variable at all. That was weird. So I can totally get rid of all of this stuff, and now my model is back to the beginning. And the only thing I really needed to do was impose weak fairness from the beginning, right? And like all of this e-tick business is gone. It's just the original thing. And so I don't need any of that stuff. And so, like, not only do I not need the init clock and that needs to go away as well, or it's going to complain. And so all of that stuff can go away now. And really my spec is just like, you know, 5 lines, 6 lines or whatever. Oh, really? And this doesn't even need to be here either. Like that can also go away. Oops, there. So really, yeah, it's like 4 lines.
Yeah, this definitely shows that you have different way of how you think about and write specification, right, in TLA. It's not programming language, right?
Yeah, I mean, and that's, you know, the good and the bad thing about it, I guess.
Yeah, it's totally cool that you can just add additional stuff and you get the liveness.
Yeah, right.
Yeah, that's cool.
I really like this example.
So you said that weak fairness and strong fairness. It's integrated inside. It's integrated. You have this WF.
Yeah.
Why? Is it so general that you can just have this as something integrated?
I am not
sure. That was strange for me.
I'm not sure how they implement this. And you know, by the way, like strong fairness is just SF, and then, you know, you tell it the variable that it's concerned about, and you know, the transition that it's concerned about. But either way, this would be, you know, same spec, but now with strong fairness imposed instead of weak fairness. But like I said, in this case, they're equivalent, so it doesn't really matter which one you choose. Yeah, so I don't know, like, the back end, what it's doing to like, you know, do this, but, you know, it's there, whatever it is. That's not something I've looked into yet.
Oh, so you say weak fairness and variable, and you supply another specification.
So you give it
these are the arguments.
Yeah. So you do weak fairness underscore whatever goals, kind of just like with this business here.
Okay.
And then you tell it a transition or step. They call it step.
Okay.
Yeah. Yeah. So then basically it's asking like, you know, if this transition that you've put here is continuously enabled, then I'm going to take one of those steps eventually. Yeah. But like, how does the model checker use this information? I have no idea.
I mean, this looks very nice. You just say, you know.
Yeah, well, right. Yeah.
I mean,
yeah. There are kind of two ways to proceed, right? You either start looking into it and spending hours and hours of your time trying to figure out like how exactly this works, or you know, you just accept that like some really smart people have been working on this stuff. I mean, you know, Leslie Lamport has like a Turing Award and stuff. I mean, like you can't trust him. I don't know who you can trust.
I would definitely think about how this like simple model can be generated in this fashion in Scala. I mean, in this way to just translate a tick without anything else, right?
Yeah.
This should be pretty easy.
Yeah.
But I'm not sure what does it mean to translate this fairness part.
Yeah, I also am not really sure. Yeah, because you don't have any kind of like control over temporal properties in Scala, right?
I mean, you can ensure that eventually you will call something in recursion, right? If this etic is a function, you must say, oh, but the end of this of the whole process, when all the other variables are changing, I will call it again. You know, And, you know, that's it.
Yeah.
I mean, this looks like in this simple case, but.
Yeah. Yeah, I don't know how you do the weak or strong fairness in Scala or anything like that, but sure got it in TLA plus.
Yeah, I like your example. It's very simple, but you know it's giving lots of way of how TLA works. So.
Yeah, and the thing about it is it's that's more or less all there is to it, right? Like we've talked about basically all of the aspects of TLA plus, like other than all of like the importing modules and like hiding variables and instantiating modules in like one you're currently working in and doing this thing they call refinement mapping. Other than that, we've discussed all of the aspects of TLA plus in just that one example, which is why I thought it was really cool.
Yeah, this is super cool. I mean, this seems like very simple and
right, I know, but also very powerful, which is good. Cool. Yes, I think I got to get going here. But yeah, I don't know if you had any questions or anything to wrap things up.
Oh, I asked you many questions. So yeah, thanks for all the answers.
Absolutely. It's my pleasure.
Yeah.
Cool.
I started watching Leslie Lamport videos, so I didn't watch everything. So I would like to go to all and.
Yeah, cool. Yeah, they're really good. I feel like he did a great job of presenting the information, and he goes through a lot more complicated examples than I did here. I mean, he even goes through an example of his Paxos algorithm showing. I forget exactly what it was. He might have been talking about safety, or he might have been talking about liveness there, but I don't specifically remember what it was.
Yeah, he was mentioning, but I couldn't understand like from your example, it's much easier to understand. I mean, he was using the whole partial specification, which was not very easy to.
Yeah. Right. Yep.
Cool.
All right, guys. Well, I'm gonna head out. It's been good.
Thanks.
See you next week.
See you.
Take care.
Yes.
Bye-bye.
See you.